So this is the formula. For example, it is the formula for the percentage of cold work, extent of cold work. So more the cold work or the more the deformation that we have given it, higher the strength it would attain. Okay. To see the example, you can see this graph where as you go from the left hand to the right hand side on the x-axis, your percentage of work or the percentage of deformation of the material is increasing from 0 to 70%, and you can see how the strength of each material is increasing. Okay, you see this, okay, and you see this, okay, and you see this a lot of improvement in the strength simply because of strain hardening. Okay, similarly here, and quite interestingly, if you see the stress strain diagram of any material, okay, metal, what you have Young's modulus, and beyond that you have yield strength, right? And from the point of yield strength, if you see until the ultimate tensile strength, what is the slope of the curve? Okay, it is typically, of course not always, there are exceptions, but in general it is having a positive slope, right? That means it is strain hardening actually. That is where the permanent deformation is taking place, right, from yield strength. Okay. So from yield strength onwards, if you see the stress strain diagram, why it is having a positive slope? Because the material is strain hardening and you need more and more stress to deform the material. That is why you have a positive slope there until the ultimate tensile strength point. Okay. That is a simple thing to observe. Okay. Right. One more important strengthening technique of any material is strengthening by precipitation hardening, or we also call edge hardening. Okay, and of course, unlike all the previous techniques, this technique is not by design. Okay, is applicable to all the metals. Okay, we have only certain alloys. Okay, to which actually we can apply this technique. That you will know why and so on. Let us now first see what is precipitation hardening. Okay, we know any solid solution, right? You give any two elements. Okay, you have a predetermined, a constant amount of B that can go into solution A. Okay, if you try to put more and more of B into A than what it can take, we call it supersaturated solid solution, right? Now we already know in salt and water, if you try to induce by stirring, okay, or by increasing the temperature, if you try to put more and more salt, you make it supersaturated and you leave it there for some time, okay, stationary, okay, give it enough time. What happens? Slowly precipitation starts, right? All the small particles, salt from the solution will precipitate out, right? It comes and nicely it will settle at the bottom, right? What is happening? Precipitation is happening, right? That is in liquid. In solid, can it happen? Yes, that happens. You take a supersaturated solid solution of, okay, any two elements, say very classical example is aluminum and copper, and you leave it at for some time, then what happens? The supersaturated copper, okay, in aluminum solution, okay, precipitates out, okay, and if it is liquid, it will settle at the bottom, but in solid it cannot go to bottom, right? So it will precipitate out and it will be there everywhere in the matrix, okay, in the aluminum matrix. Okay, you have the solid, right? So it will spatially at every place the copper will come out of the solution and exist as a different phase altogether. Okay, that's CuAl2 phase. Okay, it is a precipitate. Okay, a finer precipitate. Okay, very fine size. That means now what you have? You have very fine aluminum, right? Very fine copper, CuAl2 for small particles, and these small particles will obstruct the dislocation motion. Okay, again I am coming back to the dislocation movement because that is what is connected with the strengthening of any crystalline material. So what happens? These small precipitates that come out of a supersaturated solid solution will obstruct the movement of the dislocation, hence improving the strength of the material. So why it cannot be seen in every material, because not every solid solution you can actually make it. It is very difficult to make a super saturated solid solution, right? Of course, you can make salt and water, but solids very difficult, right? So unless it permits, okay, unless you have that kind of design. For example, you see this particular diagram, okay, which represents, you have here, let me point, yeah. So a sufficient amount of B that goes into A in this region, right? Alpha is nothing but solid solution of, okay, B in A, okay, that means small amount of B, but mostly it is A, okay, that means B is solute, A is solvent, right? Now how much it can go? It can go sufficient amount of B can go at this temperature, but as you come to the room temperature, the B is reducing in A, that means it will come out as the precipitate, okay. So essentially what you do, you take a specific Li, this Li of A and B, okay, assume it is aluminum and copper. So take copper will be, then here it will be 5%. So roughly you take about 4 to 4.5% of copper, okay, in aluminum, and that is this alloy, and heat it. If you heat it to this temperature, what happens? You have a solid solution of copper in aluminum, right? Now you don't cool it slowly, okay, rather quench it to this temperature. Now what you have, if you come slowly in this direction to room temperature, what happens? The copper that is there in this, okay, here is very high, and as you come down, you see the copper percentage is reducing, right? It cannot hold so much of copper, okay. That means all the remaining copper will come out, okay. But if you go very fast, you are not allowing the copper to come out immediately. That means what you have here, you have same composition like here, that is aluminum 4.5 copper, but copper is there in the solution. What does it mean? It is a supersaturated solid solution here, right? Now this supersaturated solid solution, okay, you can leave it, okay, for some time. Then what happens? Slowly that copper will precipitate out as a small particles, okay. Of course, it is not pure copper, it is CuAl2, okay. It is a different phase, we call it theta, okay, theta phase, okay. So that will actually act as an obstacle for the dislocation motion, improving the strength of the material, okay. So we have different steps you have to follow. For example, you take aluminum 4% copper, you first solutionize the treatment. That means solutionizing means what? If you see the diagram again, you bring it to this temperature. That means it is a solid solution of, okay, it is alpha, means solid solution of B in A or copper in aluminum, okay. That is the first step. What is the second step? Quench it, okay. If you quench it, then you have supersaturated solid solution, okay. Next, I said just leave it for some time, that means considerable amount of time, that means you will have precipitation happening and that will strengthen the material. But unfortunately, this takes a lot of time to occur naturally, and in many of the cases it may not naturally occur, this precipitation. That means you have to supply some external energy, okay. That is where, okay, you have to heat it to some high temperature, okay. This aging treatment, you will not heat it to the very high temperature, you heat it to, say, depending on the material, 200 degrees and so on, and keep it for some time. Then the precipitation actually process will be faster, and you will have sufficient strength, that is because of this precipitation, and you have to stop that at a particular predetermined time, so that you will not have very big precipitates, because this precipitates should be very, okay, of some optimum size, so that it will give maximum strengthening effect. And if these precipitates grow very big, then again your strength will reduce, okay. That is why you should be very careful, okay. This aging treatment we call at elevated temperature should be done for a precise time period, so that you have optimum size of the precipitate, so that you have maximum strengthening effect. And if you see a typical age hardening treatment, what is this? You are heating it, solutionizing temperature, and keep it for some time, so that you have all the homogeneous heating the entire material, okay. uniform heating. Once the material entirely solutionizes, entirely of same temperature in equilibrium, then you quench it suddenly, okay, to a very low temperature, okay, to typically to room temperature. But if you leave it here, some materials may naturally age with time, but it may take very long time, and some of the materials may not precipitate, naturally. Then what you have to do? You have to heat it again to a lower temperature, not as high as solutionizing temperature, but some elevated temperature, so that precipitation can happen very fast here, and you stop it precisely at a point where you have sufficient size of the precipitate and cool it down. Okay, that is what we do. Okay, now you have, if you see the strength of this material at this point, and initially you have sufficient, it is appreciably increased, okay, to a large extent. Okay, yeah, you see here you have entirely solution, okay, in a single phase alpha, that is you have all the B went into A, okay, or copper went into aluminum solution, aluminum lattice. Okay, now you quenched it. Here also you have only alpha, but SS means super saturated, and now you again leave it at a higher temperature, so that slowly all these small dots are precipitates, okay, CuAl to theta phase. That will act as strengthening medium. In other words, it will obstruct the dislocation motion. That is why you have higher strength in this particular case. Okay, yeah. So small discussion on the tensile properties, because you already know the tensile test. You will be having a specimen of specific size, a standard size, ASTM standard, or is a very famous standard, and you have to follow all these dimensional rules. Okay, you have a gauge length here, and you have shoulders. Okay, and of course this is a schematic of a universal tensile testing machine. You have the specimen here, and you have extensometer to measure the strain. Okay, and you have load cell that will determine how much load it is being applied, okay, to find out what is the instantaneous stress. Okay, and when you conduct the test, you will have stress strain diagram that I need not mention here how it looks, but from this you can obtain Young's modulus. Okay, you can obtain the yield strength, you can obtain the tensile strength, you can obtain the strain hardening behavior, you can obtain the fracture strength. Okay, and you can also obtain the ductility. Okay, you can also obtain the toughness, that is the area under the stress strain diagram. You can obtain the resilience, which is the area under stress strain diagram up to the elastic limit. So all these things, vital information about any material can be obtained simply by conducting a tensile test. And I am not iterating so much, or not discussing so much, simply because you already given assignment on this, and I hope all of you will understand and write the assignment and submit. And for your examination, I hope you prepare whatever assignment you prepare on this tensile properties. Okay, and yeah, so this is the tensile stress strain diagram, if you see. Okay, so up to here you can assume it is proportional, it is linear, and the slope of this is the Young's modulus, okay, which is a measure of stiffness of a material. Okay, and of course, if you as we have a discussion in the classroom, from physics point of view, the definition of elasticity is the resistance for the material deformation, and that means the slope will be a measure of elasticity there. Okay, but here from the engineering point of view, we basically talk elasticity in terms of the strain. Okay, that means how much strain we got. Okay, more the strain you have, more the elastic we call it. Okay, elastic strain of a material more means its Young's modulus is less. Okay, stiffness, okay, is on the other hand the measure, Young's modulus is a measure of stiffness, okay, of the material, because its ability to resist deformation. Okay, okay, that is stiffness. Okay, unlike physicists who call it elasticity. So both are correct in their own context, please don't get confused. Okay, so more higher the Young's modulus,